So what are the loads acting on the whole body? Yep, full force vector here. I'll call that, oh, let's number these. Call the foot 1, the body 2. I always do that. Yeah. Okay, so then that would make this the force on 1 by the ground. What other forces? Well, so here we're isolating the whole thing, so that's internal. We're shrink wrapping the whole thing. So all that happens inside the shrink wrap and we don't care about it. Okay? Yes, so we're including the cable is part of what I'm isolating here. Okay? So there's no cable tension in there either. Okay, so mg, that's 784.8. Okay, so when you isolate everything, that's all there is. And so when you isolate everything, if you leave that cable tension out, this is a 2-force body, which means that these have to be equal and opposite along that line between them, right? And right here, so you know that from this free body diagram, you can figure out what P is. Okay, so right away we're going to be able to find P. It's not important that you notice that, but I'm just trying to help make these connections.
You're saying it's perfectly balanced,
right? Right. That's right. Yeah, everything in this class is perfectly balanced. You know. Okay, what loads are acting on member 2?
Gravity.
Yep.
Force of the ankle.
Yep. And we're treating that as a pin joint, so that's a force vector.
Tension.
And what's the name of this force vector?
2-1.
Yep. And then we have this cable tension. I'll just call that T. We know the direction, so we're representing it with a scalar, which means we're not going to use, if you use a scalar for a variable, you don't use that AB subscript notation, okay? And finally, the foot.
Force vector 1g.
Yep.
Force vector 1, 3.
Force, yep. Right, and then this is the same tension T as this one. Okay, so let's first isolate member 1. Why don't I do this one and then I'll have you guys work on the next one, the next example we do. So this is the free body diagram. So let me draw it again. Oh, sorry, yeah, sorry. That's right. Isolating the whole thing. Okay, so start the table. This force F1G, let's call that the about point. So that acts at A, so negative 0.15, negative 0.10. Well, so that's also the about point. So rho is 0. The force is 1gx, 1gy, and it doesn't produce a moment about that about point. And then the gravity force acts at this unknown p at a height of 1.2. Same about point. So rho is p minus 0.15 and 1 point. Yes, thank you. And the force is 0, negative 784.8. So you get negative 784.8 times p plus 0.15. And you can see that 1.2 never came into the calculation for moment. So really, I gave you more information than we even needed at the start. I could have said we don't know anything about the center of mass, and we could have calculated whatever we needed. So Newton's second law says F1gx, F1gy plus 0, negative 784.8 is equal to zeros. And the moment equation says negative 784.8 p minus 117.72 is equal to 0. Okay, so just like I said, like if you sort of look at this and reason out that it's a two-force body, you'll be able to find that p. You can see the math tells us the same thing. Like we can solve for that force vector at the point A, and we can solve for p. We have 3 equations, 3 variables. So F1g is equal to 0, 784.8, and the point P is 117 divided by 784.8 is 0.15. Negative. What? Where?
Negative 0.15 plus 0.15 equals 0. And it's, a number.
Oh, yeah, you're right. Yep, you're exactly right. Okay. So now we've solved for that variable, and now we can go on to isolating individual bodies. Usually with structures, there's at least one member that you don't have to get to because you get enough equations. Let's isolate the foot, and I think we're going to see that that's all we need to do. So the foot is member 1. And it's probably just as fast for me to draw it again, but I'm going to do this because technology's cool. Okay, so let's write the table for this. The location of that point A is negative 0.15, negative 0.10. For an about point, oh, did we already calculated 1g, didn't we? That's what we just found, right? Yeah. Okay. So for an about point, I guess let's choose the ankle joint. So 0.15, negative 0.10. The force is 784.8. And the moment then is this again, right? Negative 117.72. Then this reaction force is at 0, 0. So rho is 0, 0. The force is 12x, 12y. The moment 0. And now we have to deal with this tension. So in order to do that, since we're not given the distance from this line of action to the ankle joint, we're going to use a unit vector. Okay, so for the tension direction, we know that that force is going to go from B to C. Okay, so it's going to be 0.02, 0.3 minus 0.06, negative 0.01. So you get negative 0.04, positive 0.31. Okay, that's a vector in the right direction. And now we have to make that a unit vector. So unit vector calculation says this is negative 0.1280, positive 0.9918. Okay, so that force acts at the point B, which is 0.06, negative 0.01. The about point is 0, 0. Rho is 0.06, negative 0.01. And then the force vector is this times that tension T. So negative 0.1280 t, positive 0.9918 t. And if you do that cross product, you get, I believe, 0.05823 t. So Newton's second law says 0, 784.8 plus 12x, 12y plus negative 0.1280 t, 0.9918 t is equal to zeros. And the rotational equation says 0.05823 t minus 117.72 equals 0. Okay, so in this case, we only had to, we have 3 equations. Our variables, I guess let me write them. So our equations are 12x minus 0.1280 t is equal to 0. Then we have 12y plus 0.9918 t is equal to negative 784.8. And then the third equation is should that be positive? Yes. So 0.05823 t is equal to 117.72. And our list of variables, 12x, 12y, and t. Yep. So yeah, now we have 3 variables, 3 equations, we can solve it, and there's nothing that we want to find that isn't represented, either, itself or with Newton's third law. So you can solve this one by substitution pretty easily, but I'll do it this way because I like to make everything hard. So 1, negative 0.1280, and then 1, positive 0.9918, negative 784.8, and then 0.05823, 117.72. And I did get answers for this before. They sort of surprised me how high they are. So check this and tell me if you get the same thing. So I got a tension that's equal to 20,000, 216. I assume that's round off error. Just kidding. You know, like everything should be 20,000. Forget you guys. Oh, okay, okay. Oh, okay, good. What is it? Okay, and what did you get for F12?
I got an F12X of like 258. Yep. And an F12Y of 2789.
Okay.
Oh, negative.
2789? Yep. Okay. Well, that makes more sense to me than the values I got. Okay, so what that says is if we isolate these objects, now this isn't running or something, this is just standing on your toes. Your Achilles tendon has a force in it of 2,021 newtons. And your foot, like the foot part of your ankle joint, feels a force of 258.6, negative 2789. And then on your leg, this is F21, so this is negative 258.6, positive 2789. And the force applied by the gastrocnemius muscle to your leg is 2021.6, pointing that way, which is, you know, a pretty impressive amount of force considering that this person just weighs 784 newtons. This is like, what, four times body weight? Just 3. Don't try to exaggerate. I don't know. I'm not good at arithmetic.
Well, the ankle joint every 4.
Okay, yeah, right. Yeah, 3 times the weight in the Achilles tendon, which explains why you get Achilles tendonitis when you jog too much, you know. Even when you stand too much, it seems like you should get it. And yeah, 4 times your body weight is what your ankle joint feels just standing there. And so that's just using the method of structures. And this is exactly the kind of calculation that biomechanists do to calculate joint forces and muscle forces. I don't know. I find this stuff interesting because I did this stuff for a long time. And then, so sports scientists do this, except that they're doing it in dynamic cases. So instead of using these equilibrium equations, they have MA on the other side, you know. That's the only difference between calculating this force when a person's in this position standing and when this person's in that position on a diving board just about to take off or something, or landing from a jump or something. Okay, the next thing that we're going to do, I'm not going to do it today, but I'll just draw the picture, is we are going to do a structure that looks like this. So the structure is simple. It's just an equilateral triangle. All the lengths are 1 meter. All the joints are pin joints. And this one's attached to the wall to keep it from tipping over. But instead of applying an individual load, we're going to do a distributed load here. Okay, so that's the problem. We're going to try to calculate those reaction loads. And if you have time to work on this, see if you can figure out how to go about it. It's really just putting pieces of what we've already done together. I know you're studying for the exam and stuff, but if you have time, this is what we'll do next time. And I think I'll have you break into pairs and groups and stuff and work on this. Oh yeah, that'll be Thursday, right?
So really next time is the test.
Next time is the test, that's right. Maybe I'll do this in the back. I'll lecture while you're taking the test.
That'll be so helpful.
Yeah.